sum would be 0. The phases would equal one magnitude of current, the neutral would equal another. They would be equal in magnitude but opposite in direction. They would cancel. The principle is very much like putting a clip-on ammeter around an extension cord, say for your lamp in your home, or the PC cord, the power supply going to your PC supply. It is a phase conductor or a line conductor and a neutral. If you were to put a clip-on ammeter around that conductor, then your clip-on ammeter would read 0. Zero sequence sensors operate the same way. A zero sequence sensor, as we said, goes around all phases and the neutral conductor, such that if there was a phase to ground fault, then the current would flow in return path outside of the sensor. It would go outside, return into the neutral via the main bonding jumper ahead of the sensor, thereby bypassing the sensor. And the sensor would sense current magnitude different other than 0, put an output to a ground fault relay. The ground fault relay would actuate, operate a shunt trip coil. The shunt trip coil would trip this power switch or circuit breaker. These are external devices. They are not part of the circuit breaker or part of the power switch. They require an external sensor. They require an external relay, an external trip coil, as well as a reliable source of control power. Remember that the control power will be derived from the phase conductors that are providing also power to the fault. So you have to have a reliable source of control power during times of a fault, such that your control power stays high enough to operate the shunt trip coil. The other type of ground fault protection system is what's called residual sequence sensing. Residual sequence sensing is one in which there is an individual sensor around each phase conductor and each neutral. On a radial system, you would have 4 sensors, one per phase, one per neutral. The operation is exactly the same. However, with residual sequence sensing, those are usually associated inside of the breaker, and there's an external neutral sensor. In many cases, residual sequence sensing is called integral ground fault, in that the phase sensors inside of the breaker and the neutral sensor outside of the breaker has an input into the breaker, such that the summing module is happening inside the breaker and the trip coil is inside of the breaker and does not require an external power supply. The current output of the sensors actually drive the trip coil function. It's called integral ground fault. It doesn't require an external power supply, for example, a control power transformer. These are very reliable and are not affected by any changes in the line voltage due to an arcing ground fault. In addition to that, they're often used to power electronic trip units in which their operating ranges are very tight and are very sensitive and to coordinate very well. Let's talk a moment about coordination. If you have multiple sources of ground fault protection, it's extremely important that those settings be established by a professional engineer of record, whether one is part of the engineer of record that designed the system or a consulting firm after the fact that's employed to provide the settings. Square D ships all of its circuit breakers on minimum settings for the maximum available protection for the customer. What we often see in the field is where the settings are not properly coordinated and where someone has just randomly selected settings in order to perhaps avoid a nuisance trip situation or have the impression of being coordinated. Selective coordination settings require a study by a professional engineer that has to look at variables such as the size of the power system, the available fault current from a local utility or energy provider, and the impedance in the return path and the impedance in the circuit. Then a study is performed to provide the right settings so you guarantee selectivity, and the systems must be tested after the settings are provided. But to randomly select settings on breakers is a good way of ensuring that your systems will not coordinate, such that when you have a downstream fault, you can have more breakers upstream operating such that more of your power system is tripped offline and your services can be interrupted. Now, multiple-ended systems have the same issues as radial systems in that they must be coordinated, they must be tested when they're first installed, and they must be properly installed. However, the difference between multiple-ended systems and radial systems differ in that with multiple-ended systems you have additional main bonding jumpers and additional system ground bond jumpers. What happens is inside of the service equipment where all of your power sources are provided, say for example you have a main system where you have two utility sources and a common load bus, or what's called a main tie main system where you have two sources and a tie breaker and two separate load buses such that the tie breaker can be closed to feed either one of the load buses, either A, B, or 1 or 2. Respective to each main breaker, there is a neutral ground bond downstream. And because you have two main bonding jumpers, the neutral bus inside the service equipment will actually be paralleled with the ground bus inside the same equipment, such that any imbalanced current will circulate inside the equipment between the neutral bus and the ground bus. This is quite normal. It is harmless and won't affect anyone. In fact, I've proved it myself on several occasions in our testing lab where we've actually injected as high as 60,000 amps inside of a ground bus and exposed bare skin to the steel as well as taking measurements. There is no current outside of the gear, such that the concern is, we cannot have circulating current in the ground bus. It is quite normal inside service equipment where you have multiple-ended systems. It's hard to avoid. However, as far as ground fault protection, you still employ radial zero-sequence sensing, either by zero-sequence sensors or residual sequence sensors, in order to provide ground fault protection. However, all of your relays and all of your operating coils and your sensors, the output of your sensors, be it a current transformer or a current sensor, are all interconnected in what's called a differential configuration. And we call it a modified differential because it varies a little bit from traditional bus differential. But modified differential systems are variations to the standard bus differential systems that have been employed in medium voltage systems for decades. And a modified differential ground fault system during normal operation where you have circulating neutral currents or imbalanced neutral currents, the vector sum of all the currents equals 0. And during an actual phased ground fault condition, you get selectivity in the right specific zone. And it matters not how many sources you have or how many feeders that you have. A differential ground fault system will guarantee that you have zones of selectivity. The other benefit of having a differential ground fault protection system, as produced by Square D, is that during in a system that you have a main tie main, such that you have a main breaker and a tie breaker that have ground fault protection, under the standard system, if you have a main breaker, say feeding source 1, and you decide to close the tie breaker to feed the load equipment or load breakers on load bus number 2, then you have to adjust your settings in order to account for the tie breaker being inserted into the circuit, where you have a main feeding a tie and the tie feeding the separate loads on load bus number 2. In a differential ground fault system, that tie breaker actually acts like a main breaker, such that the ground fault settings can be the same for the main and the tie breaker, such that you do not have to interfere with the coordinated settings and allow a gap to insert a tie breaker in the future. The tie breaker functions as a main breaker for load bus number 2, and during a fault downstream in that zone between the tie breaker and your feeder breakers, if a fault were to occur, then the tie breaker would open and the main breaker upstream would be guaranteed to stay closed, such it would only interfere with that zone. That's the benefit of a differential ground fault protection system. It provides